Hi, I'm Tom Flynn, editor of Free Inquiry. I'm here at the Center for Inquiry Television Production Studios. Just down the hall, we're having a major conference on the future of naturalism. And it's my honor to have here one of the distinguished speakers. Dr. Victor Stenger is Emeritus Professor of Physics at the University of Hawaii and Adjunct Professor of Philosophy at the University of Colorado. He's written quite a number of books, including the New York Times bestseller with the provocative title, God, the Failed Hypothesis. Dr. Stenger, great to have you with us today.
Well, thanks for having me, Tom.
Oh, it's my pleasure. You've written a whole series of books basically making an extended case why what science tells us about the universe shows us that we don't really have a need for supernatural explanations.
Yeah, that is basically the theme, because you find a lot of people in medicine, in religion, of course, and the supernaturalists who promote the paranormal will look at science and think they can find in science good reasons to support their particular beliefs, and that's always disturbed me right from the beginning. And so my books have been basically on the theme of looking at some of these claims and in a critical way, in a hopefully honest way. Let's treat them and ask, what is it that science really does say, and can these conclusions be properly drawn?
Very good. We've seen probably in the years since World War II sort of an explosion of theistic philosophers who are claiming in kind of a new way that they can look at the world, they can look at facts and patterns that are out there and say, aha, here is existence for God. And certainly we saw this in the 1970s with people who were claiming to find within quantum mechanics wiggle room in which an otherwise mechanistic universe would support free will or would leave room for divine creativity. And you addressed that in one of your earlier books, didn't you?
Yes, there was a book called The Unconscious Quantum that came out in 1995 that I addressed. I went into the quantum mechanics in some detail and looked at the claims that were being made. And the interesting thing is that's an issue that's rising up again right now with both the new spiritualism that's marked by books such as The Secret, the book and film The Secret, which claims that you can be what you want to be, do whatever you want to do, you can get all the success you want in life, all you have to do is really think about it. And that's been a theme that's been running in this for a long time, going back to a lot of the works of Deepak Chopra, where we make your own reality, quantum healing, the timeless, ageless quantum, and so on. And it's based on a misinterpretation of quantum mechanics that goes back through the early days of quantum mechanics, when there was a lot of philosophical work being done on what it really meant. And it seemed to people that that consciousness was somehow coming into it, and some very famous physicists were making such statements that the world is kind of the way we want it to be, and we create it. And this came about from something in physics that's called the wave-particle duality. That light was originally thought to be a particle by Newton, and then in the 18th century it was discovered that it was really a wave phenomenon, and then in the 20th century it was found to be a particle phenomenon after all. In fact, the wave phenomenon didn't go away, it's just that it seemed to be both.
I think I need a scorecard.
Yeah, so light was both a wave and a particle. And then they found that electrons, for example, and other particles were also waves. They seem to have the same wave-like behavior. So this came to be known as the wave-particle duality. Furthermore, what it seemed to be was that whether a particle was a wave, or whether an object, let's say, was a wave or a particle, depended on what you decided you wanted to measure. If you wanted to measure a wave-like property by doing an interference experiment or something like that, that waves interfere with one another, then you saw waves. And if you wanted to do a particle experiment where you localize something, you get particle behavior. So it seemed like you could control that. In fact, you could do it after the particles left the source. You could do it with particles or with light, let's say, that left a galaxy a billion years ago, and then decide to take that light and make it either a wave or a particle. And so that was what led to this notion that the mind is really controlling what something is.
Right, because this also ties in with the Heisenberg uncertainty principle, doesn't it? That
yes,
you can know the velocity or the position, but not both to a high level of accuracy. And whichever one the experimenter chooses to measure affects the outcome.
Yeah, yeah. And of course that, to a certain extent, made sense, because in order to observe anything, you have to interact with it in some way. While looking at the moon doesn't affect the moon, when you look at an atom, you shoot light at the atom, you can bounce the light around and destroy the atom. So, but you know, that part of it is perfectly fine. That makes sense. But changing the actual nature of the object is what we're talking about here. That making reality just by thinking about it. And that's what led to these notions that I felt like I have to address.
Sure. And ultimately, you had people going on the Oprah show and saying that the universe wouldn't even exist if people weren't here to observe it, because it's our act of observing it that magically, what they call, collapses the wave function.
That's right. That's the other aspect of it. In fact, there's another feature of this. This is something that Einstein objected to a long time ago. He had a lot of problems with quantum mechanics, and he gave the example of what's called wavefunction collapse. The wave function is what you use in quantum mechanics to mathematically represent the particle, and he said, suppose you don't know where a particle is to begin with, then its wave is spread throughout the universe. And then you measure that particle, and now you know where the particle is, so that wave has collapsed to the size of your detector. And he says this happens instantaneously all over the universe, faster than the speed of light. He called that spooky action at a distance. And so this was a real problem. At least it seemed to be a real problem for people for a long time, but it really isn't. And anytime you want me to tell you why it isn't, I'm happy to tell you why it isn't.
Something tells me this will involve a blackboard and a whole lot of mathematical operators.
No, the basic experiment that you do when you measure the wave property of something, the wavelength. Let's say you want to measure the wavelength of a wave. You could do this with a water wave, and it was done as far back as 1800 by a man by the name of Thomas Young. It's called the double slit experiment, where you shine light through two narrow slits, and then the light that comes out of these slits interfere with one another, just like two water waves interfering. And where the peaks, imagine a water wave, when you have a peak, if the peaks line up, you get constructive interference. And when the
waves get higher.
Yeah, and when the peaks cancel, you have the positive peak and the negative on top of one another, then they cancel. And this gives you on a screen, let's say, a pattern of bright and dark lines. So this is what you get. And when you see that, you can measure the distance and so on between those bands and measure the wavelength of the light. Or in the case of electrons, you measure something comparable to the wavelength of light, the Broglie wavelength, it's called, the wavelength that particles have associated with them. Now, here's what happens. As time went on, and we had better and better experiments, we could measure individual photons. You could use detectors that could measure an individual photon. So instead of having, say, a photographic plate on the wall where you're shining the light, what you do is you have a whole array of little photon detectors. The photon is the particle of light. And what you find is that you get individual hits in this double slit experiment. You get individual hits all over the detector array that look random at first. Particle by particle, photon by photon. It looks random. And then all of a sudden a pattern starts to build up. And the pattern is this bright and dark series of hits. And in other words, the wave that you're seeing is not a property of the individual particle at all. It's a statistical property of the whole beam.
You average out this huge number of individual hits.
Yeah, and that's how it averages out into this pattern. And so what you were seeing, and this is what's described by the wave function in quantum mechanics, is not the motion of an individual particle. It's the motion of the whole ensemble. It's the average behavior of the whole ensemble. And this is what the wave function means in quantum mechanics. It's a probability rather than some property of a particle. It's a probability that you'll find a particle at a given place.
So
and in either case, it's a particle. You see, you're measuring particles all the time. It's the particle that's the fundamental nature of the object that you're seeing, and the wave has to do with mathematically representing its distribution, the distribution of a large number of the particles.
And this would be one of the ways that the quantum mystics would go wrong, looking at these statistical properties of a large number of particles and trying to infer to the individual particle, and then draw some moral that, oh, here's where human creativity comes from, here's where the mind of God can have free play, whatever it might be.
Yeah, but you see, the basic result of this is that the mind isn't controlling the nature of the object. The nature of the object is it's a particle, and that's it. It's a chunk of matter, and the mind has nothing to do with it.
Very good. Let's jump up ahead a little bit closer to our own time. There's been a great deal of excitement in the scientific community and certainly among professional theologians with ideas like fine-tuning. Supposedly there are a series of physical constants that pretty much had to be almost exactly as they are, or we wouldn't live in the universe that we do. Basic chemical reactions wouldn't go forward. Matter might not even exist. And that supposedly it's so improbable that these 5 or 6 core variables happen to have exactly the values that we do, that therefore God must have designed it that way just for the purpose of creating a universe where people like us would come to exist.
Yeah.
My baloney detector is reading really high right about now. How about yours?
Well, you wonder why God would then put us on this tiny planet in this vast universe that's mostly empty space, have had a universe last that they took billions of years for us to even come about. So all those billions of years, there was no humans. Humans were so important, you would think that he would have made it possible for us to live every place in the universe, live in space for that matter. Why couldn't God do that? God is God. He should be able to do anything he wants. So
he could have a really wicked sense of humor.
Yeah, well, that's what some theologians claim. But I don't think that God's pretty funny myself. Some of the things he's done to the rest of us, if he exists, to the human race and suffering and everything. That's not a very amusing God. But besides that, there are a couple of fundamental flaws with the argument. First of all, it is true that if the constants of physics were slightly different, the universe wouldn't be the way it is, and life as we know it would not exist. But that's not that doesn't mean that there isn't some other kind of life. But we really don't know. Since we only have one universe and only one kind of life, we don't know what other types of life might have been possible with a different set of constants, with different laws of physics, and so on. And there have been a lot of calculations and speculations made about different kinds of universes. I've even done some of this myself, where I varied the constants of some fundamental constants by many orders of magnitude, and found that most of the time you still were able to have a universe that has a long-lived stars. And once you have long-lived stars, you've got time for life to evolve, no matter what the kind of chemistry that life might follow. So that's the first point. The first point is that life could take on many different forms with different sets of constants, and it's wrong to assume there's only one possible form of life, the carbon life that we have. But there's other stuff as well. I mean, many of the constants that they talk about are not really a problem at all. Let's take one example that they like to give is the big difference there is between the strength of the electrical force and the gravitational force. If you take a proton and electron, and it doesn't matter how far they are apart from one another, the gravitational force is 39 orders of magnitude weaker than the electromagnetic force. And if that weren't the case, you wouldn't have long-lived stars. If the gravitational force were comparable to the electrical force, then stars would collapse long before they had any chance to have planets and certainly life to form. And similarly, if there are a number of examples like that. But what people who talk about this, the problem is that people who talk about this don't really know a lot of physics. And they don't know that when we talk about these quantities being constant, they're really not constant. They're just very slowly varying. They vary over millions of years. They don't change at all, but they do have some energy dependence. And when the universe was young, it was a lot hotter, a lot more. The particles were moving around a lot more energetically than they are now. And in fact, you can conceive of the most likely scenario in which all these forces early in the universe, when the universe first formed, all these forces were equal. The sort of natural way you would expect them to be.
We're talking like 13 billion years ago.
Yeah. And then what happened is, as the universe cooled, and incidentally, this is not just speculation. This is the theory tells us this. The current theories tell us that the forces separated, and now they're sufficiently different so that we have the kind of universe we have in which stars last for a long time, and so on. And as I said, you could get that property for a large variation of parameters. They didn't have to be exactly what they are now. So there's many arguments like that cause the whole scenario, the whole argument to fail. And then the final argument that a lot of people don't like, a lot of theists don't like, and even some scientists don't like, and that is the possibility that there are really more than one universe, that there are multiple universes out there that have different sets of laws. And they say, well, that's speculation. We can't talk about that. We don't know how to detect the presence of such universes. But they are predicted by existing cosmological theory. Cosmological theories now that have done a very good job of explaining observations. If you extend them, if you extrapolate them, they do predict that there are other universes. And they would have, we just happen to be in the one that we were suited for. That is, we happen to evolve in the universe that
in a universe whose characteristics were such that we could evolve.
Right,
there,
just the same reason we evolved on Earth rather than on Mars, because our particular form of life was able to evolve on this planet.
And one thing that I've always had a question about, this idea of the multiverse is in some ways an effort to make the improbability of our being here in this universe that's right for us seem less remarkable. But let's suppose that some of the physical constants really did have to be pretty carefully within their current limits in order for us to come about. Let's say that this might have been an extremely, incredibly improbable event. Well, the probability of any improbable event after it happens is 1.000. What's to say that maybe the universe, maybe our universe being the way it is just as improbable as some of the critics say, but it happened. We don't know why it happened. We may not ever know why it happened, but here we are.
Well, you can't use probability arguments just based on the fact that some probability you calculate is very small. You have to compare it with the probability for the alternative hypothesis. Certainly low probability events happen every day. When you consider the probability that you're here, that I'm here, in the form that we have, what were the chances that that particular egg and sperm would unite, that your parents would meet, that your grandparents would meet, all the way down the line, all the accidents. Think of all the accidents.
Whole nested chain of individually
would have
improbable
taken
events.
place. Yeah, of course, we're here with 100% probability. We're here. It's the difference between the a priori and the post probabilities. And so just the fact that it's the probability is small is meaningless argument. That takes you no place. What you have to do is compare with the alternative probability. What's the probability that there's some God out there doing all this? And of course that becomes an uncalculable quantity. It could be very low. It could be just as low or even lower. I happen to think it's very low probability because it's such an absurd idea. But other people will dispute that, and I can't provide them with any calculation of that, and they can't provide me with any counter calculation.
In your book, The God Hypothesis, you did make one proposition that I think a lot of religious believers would find controversial. You said that along quite a number of possible axes, the hypothesis that the Christian God is out there or something like him and made the universe according to his design is actually a testable hypothesis. There's scientific work that we can use to illuminate that question.
Yes, that's the theme of that book. I mean, and that's why that book is unique, because most people who have written from an atheist perspective and have tried to argue that God does not exist have used the argument, well, other than philosophical arguments, I'm talking about just straight scientific arguments. The only scientific argument that's been presented up till this point was the absence of evidence argument, that there's no evidence for God, and so God is very unlikely to exist because there's no evidence. We don't believe in Bigfoot or the Loch Ness Monster because there's no evidence for them, so we don't believe in God. And of course, a lot of theists throw back the Carl Sagan line, which I wish he had never given, and that is that absence of evidence is not evidence for absence. Because I think absence of evidence is good evidence for absence, because we don't believe in things we don't have evidence for. But nevertheless, I went further than that, and said, look, the God that most people worship, the God that not just Christians, and I kind of maybe overemphasize the Judeo-Christian Islamic God, because every religion in the world believes in a creator God, and you can make an argument that if there was a creator God, there should be some evidence for that creator God. You should see that. You should see that energy conservation or something was violated in the early universe, and you don't. The cosmology of the universe looks just like it should look if there was no creator. In fact, you can even make an argument that there couldn't have been there is no memory of a creator in the existing universe, because the universe, according to modern cosmology, which, as I said, is a very well-established theory now, because it's become a very accurate science, both instrumentally and theoretically. This modern cosmology extrapolates back to the earliest possible moment, and at that point, the universe was in total chaos. So it had no organization, no order whatsoever. And even if there had been a creator, the memory of that creator would be erased.
So, and with that, there would have been no way that the creator could have exerted influence.
Influence, right.
On his creation.
I mean, the only God that's possible under that scenario is the God that Einstein always complained about, the God who plays dice. The God who started off all the chaos is a possible God. But that's not a God most people worship. It's obviously not a God you would pray to,
That's
because
the kind
he's
of
not going
God
to do
who,
anything.
kind of God who just empties out a box of toothpicks
Yeah.
and doesn't even look to see where they land.
So that God is certainly possible, but that's not the God that people worship. The God that people worship is a God who answers prayers, a God who reveals truths to humans. And those things, among others, are testable. A God who answers prayers is testable because you can do experiments on prayers, and they have been done, very good experiments, have tested the efficacy of prayer and healing, for example, and found that there's no effect. Well, if prayers worked, if prayers were worth doing, then
you should have more evidence
should
by
have
now.
it. And that brings up another point, because
Well, actually, Dr. Stenger, I'm going to have to bring things to a conclusion here.
That fast?
We're out of time.
Okay.
Time flies when you're having fun, and perhaps
That's
it's
right.
quantum mechanical and relative, but I doubt
Yeah,
that.
I think it's what they call time dilation and Einstein's theory of relativity.
It's a common phenomenon in a television studio. I'm here with Dr. Victor Stenger, author of The Unconscious Quantum, God, the Failed Hypothesis, and many other books. For the Center for Inquiry, I'm Tom Flynn.